Hello and welcome back to our ongoing look at analytic trigonometry. This is where everything starts to come together. And we've been looking at general trigonometric expressions, trying to simplify those. We've been looking at some basic trigonometric identities, trying to show that two expressions are always equal. And we are going to continue traveling down that path now. We're going to add on a few more identities, a few more equations and formulas into the mix. Motivated because we kind of need them, and then in the next few videos we'll start using those to prove new identities. And yes, we will start to need them, because when you stop and think about it, all the angles we've really computed in this class, especially by hand, have been for the nice angles, right? 30 degrees, 60 degrees, 45 degrees, or any of the similar reference angles anywhere else. And that's all we've been able to compute by hand. So if I were to ask you, say, find the cosine of 75 degrees, we might be at a loss for words. Maybe we would say, okay, well, 75 degrees, that's 30 degrees plus 45 degrees. So we have that added together in here. So I've got cosine of 30 plus 45. Well, is that not the same as cosine 30 plus cosine 45 degrees, right? Can't we distribute cosine across? And we can compute the cosine of 30 degrees. We can compute the cosine of 45 degrees. Root 3 over 2, root 2 over 2. So cosine of 75 degrees has to be that sum. Root 3 plus root 2 all over 2. My calculator says about 1.573. Well, there we go. We just found it. What's the problem? Well, the problem is cosine can't be bigger than 1, right? The range of cosine is from -1 to 1. Same for sine. Tangent, of course, can be all real numbers, but we're looking at the cosine of 75 degrees. I know right away this can't be right. In fact, if I were to crank it in my calculator, cosine of 75 degrees is actually closer to a fourth. It's about 0.259. So where did we go wrong here? Let's take a minute. Let's actually look at this and see what went wrong. Let's kind of work backwards here, work forwards, see where the disconnect could have happened. I do know that I typed that in my calculator correctly. Root 3 plus root 2 all over 2 is about 1.573. So that's good. Cosine of 30 degrees is root 3 over 2. Cosine of 45 degrees is root 2 over 2. So that's got to be good. And 75 does equal 30 plus 45. So this first line is good. By process of elimination, knowing that something had to have gone wrong, and 3 of the 4 lines are good, this line can't be right. This can't be true. Cosine of 30 degrees plus 45 degrees is not the same as cosine of 30 degrees plus cosine of 45 degrees. Cosine does not distribute. And hopefully that doesn't come as a surprise to too many people, but all the same, let's bring up the age-old debate, when can I distribute things? This is a thing I love to hate, when people tell me that they can distribute something when they absolutely can't. Right? We know that multiplication is distributive, right? I've got some number being multiplied onto a sum, that does distribute. So a onto x plus y, that distributes ax plus ay. But we recognize right away that addition is not commutative. Right? I have something being added onto a sum, that is not the sum of a sum. Exponents are not distributed, right? X plus y quantity squared is not x squared plus y squared. There's a middle term that'll pop up, 2xy. For those of you who have had algebra or will take it or are taking it now, you will get to see what happens with whenever you have log of a plus log of b. It's not log of a sum. Logarithms are also not distributive. And as we've just seen, trigonometric functions are also not distributive. And we'll see in just a minute what they are, how we can handle sine of a plus b, or how we can handle cosine of a sum. But it's not just a straight substitution. In fact, remembering the distributive property has a full name, and that full name is the distributive property of multiplication. You can only distribute things that are being multiplied on. I know we have it written cosine parentheses, but that's not cosine times 75 degrees. That's the cosine of 75 degrees. We evaluate cosine at that input. So cosine does not have the multiplicative property. It does not distribute. We have to do something else. So the time has come for us to do that something else. And I'm going to explore this pictorially. I'm going to do a pictorial proof for you here. So here I am. We'll say this is a line segment. This here points on the unit circle. We'll just say that to make the arithmetic easier. We've come to a stage in our lives where we are okay doing unit circle approach and right triangle approach interchangeably. So this length right here is length 1. So that's length 1 right there. Just again to make the arithmetic easier. We can multiply all these results by r when we're done, if that makes you feel better. But let's say I rotate by a sum of 2 angles to get here. Say I rotate by A and then by B. And so our final point, being on the unit circle, is going to be cosine comma sine. And the angle in question, the amount we're moving around the unit circle, is A plus B. So our terminal point's cosine of A plus B, sine of A plus B. And the challenge we are now going to undertake is in finding a way to get to this point using alternative means. Because here's my big triangle, right? If I were to do the right triangle approach for us right here, I now have a base of a right triangle of cosine of A plus B, a height of sine of A plus B. But I want to get there using some other means. And the other means I'm going to want to use is, okay, I'm up here now. I'm going to rotate down by B. So if that whole thing was A plus B, then that's angle B right there. And that's angle A right there. What's this point right here? How do we get that point right there? And the way we're going to do it is we're going to use this thing, this bottommost tiny triangle, as its own right triangle. And actually it's the case that this red triangle is also a right triangle. So we're going to use a whole lot of right triangles in finding how to eventually end up at this point. So let's see here. This length right here, from origin to this corner that we want to get to, this length looks to be 1 cosine B. So the length of this segment right here is cosine B. And for reference, this height right here is sine B, for this red segment there. And this does satisfy the Pythagorean theorem, right? I square the base, I square the height. I've got cosine squared plus sine squared, that is 1. So we're so far so good. But now for this smaller triangle here along the base, I've got a hypotenuse of cosine B and an angle of A. So this base length now is going to be r cosine theta, where r is cosine B and theta is A. So this length down here is actually cosine A cosine B. And this height is cosine B sine A, right? R sine theta. So our point, our midway point right there is cosine B cosine A, cosine B sine A. All right, we're getting there. We're getting there. So now we want to go from this point to this point. And we do that with just one more small triangle. So let's see here. This height right here was sine B. So that's now the hypotenuse of this small triangle. And this angle right here is actually going to be A. And that's because this was a 90-degree angle. And this angle right here is 90 minus A, right? Because all these angles in this bottom triangle is 180 degrees. So I've got 90 minus A here, 90 here. By this being a 180-degree flat angle, that has to be A. So now, this height is r cosine theta. Theta is A, r is sine B. So this is sine B cosine A. This height is sine B sine A. And if you were to put all that together, I'll see, not that point again, you end up with another way of adding all that together. So let's see how we add all these lengths together. So this was cosine B cosine A. This height was cosine B. This is impossible to do. You know what? Never mind. There it is. Right, this base was cosine B cosine A. We had two heights, cosine B sine A, sine B cosine A, and then this length right here was sine B sine A. So to go from here to here, right, the x-coordinate, the x distance was cosine of A plus B. But it can also be found by going to the right cosine B cosine A, and then back sine B sine A. This vertical distance, it is sine of A plus B, but it's also cosine B sine A plus sine B cosine A. And there you have it, a pictorial proof of the sum and difference formulas. Cosine of A plus B, cosine A cosine B, minus sine A sine B. Sine of A plus B, sine A cosine B, cosine A sine B. We didn't just pull these out of nowhere, they do come from somewhere. And that is where they come from. There's other proofs out there, I'm sure. But that's the one I chose to give you. Now we're not done, right? You know there's a cosine and there's a sine. There's also a tangent. And I'll just leave the work for you here. You can kind of gloss over this while we're wrapping up what I'm saying here. We have more formulas. You don't have to memorize them, not in this class anyway, but we have access now to more formulas. And because we have taken the time to very carefully explain where they come from, and in the next video we're going to very carefully use them, and in the video after that we're going to very carefully use them in proofs for more identities, you don't need to remember what they are, what they look like, you need to remember how to use them. Although, if you do have a future in more conceptual things, math education, some more philosophical sciences in there, then you might want to look at this and see if you can suss out the steps that were in place here. That's actually kind of neat. I kind of like what we do here. Because really all that happens is you multiply by this magic thing right here and you simplify. But we have now some formulas for all the big three. The reciprocal functions, of course, you just do reciprocals of everything. But worry about that here in a bit. So we have reached a good stopping place, I think, for now. I've got one more video for you to look at right away, and then one more still after that. So I'll see you soon.